Good morning, students. I guess I guess when I thought that we'd be getting some winter weather, I didn't I didn't plan for this really challenging time. I think I just checked the temperature and it's a balmy 18 degrees. So I feel like I've taken a trip back to Montana, which again, when I was there, I'm not really sure. I guess it maybe got maybe down to 18 or something. I just remember maybe 20 or something. So we again living in the great state of Texas, we get all weather. So if anyone ever tells you that you're just in a state where it's always hot and you know you're not used to cold weather, then you can tell them, okay, wait a minute, January 2021. Well, I just wanted to let you know that I have posted the solutions to the test. I just made another block in Blackboard right above the test one, and it's just entitled Test Solutions. So that's where you can go and just actually look at the problems that were on the test and check through the solutions. And what I'll do is I'll be going through your test and also your test work to make assessments there. So I appreciate your willingness to get the test done and to turn in your test work. That was very good. I mean, it's always a challenge with an online course to be able to get everything done, even if you have a good window of time. I know it's really tough to navigate all the different courses you have. So again, I will always give you a window of time to complete your assignments, especially when it comes to the test and be as flexible as I can be. So thanks again for your hard work and your willingness to, as they say, follow directions. I always think of Dr. Hellier, our chancellor, who is always giving us ideas about what we do and following schedules and things. And I have to do the same thing, and sometimes it is difficult. So I appreciate your hard work. Now, remember last time we talked about work and springs and moving liquids around, and that was a fairly interesting set of problems. What we want to do today is talk about center of mass, which is another application that you will find very interesting in physics and engineering. So again, these topics will come up over and over again. Now, after we complete that, that will be our last application. There is a section in your text on hydrostatic force, which again is a very interesting section. I usually try to fit in the center of mass and then I move on to chapter 8. So if you're interested in that as a future engineer, then I encourage you to read that. You will use some of the topics that we talk about with center of mass. And so it's a very interesting application. And lots of times I always say, if we have additional time, I'll go back and pick up some things, but usually the additional time is not there. Calculus 2 is very filled with plenty of topics, and we struggle to get them all in before the end of the term. But again, like I say, if you have some extra time, you should look through that. I think you'll find it very interesting. Now, for the center of mass, what we want to do is start with a more discrete setting and then move to the continuous setting. So let me go ahead and share my screen. Like I said, normally when we think about the applications, we just want to jump to the situation where we have a continuous distribution and we've got our partition and we work that way. But with the center of mass, we have to be a little bit more particular at the very beginning. But then I think it'll make sense as we move to the continuous setting and make for an easier transition. So let me adjust the chair here. And so we've got 7.6, which will be center of mass. Now, in the first setting, I'll just entitle this one dimension. So you think of this, and I guess this is very intuitive, but we think of a system of point masses. System of point masses. Move that over. Now, what we want to think of, at least in this particular case, is for every point mass, we have an associated coordinate. So for instance, we're going to think of just a real line. We'll mark 0. And what we're going to think about is a distribution of a system of point masses. And then, of course, what we want to do is to note the algebraic distance from the origin, not just the distance. We kind of like doing standard deviation. We don't want to forget the sign. So we have the origin here. So what I'm going to do is just distribute some masses. So we'll have like an M1, and it will have an algebraic distance X1. And just, we'll put several in, and of course we'll have maybe N in general, like a partition. Say an M2. And then an M3. So again, we have this distance to the origin that's algebraic. That is, it carries a sign. And say we have an M4, and then I'll just say Mn in general. And then maybe over here we have an Mn. And so what we're thinking of is understanding how this system reacts relative to the origin. And we define what we call a moment about the origin, which is basically a tendency to rotate about the origin. So we define, in this case, the moment about the origin. And this is a standard notation. I always say that everything's standard when it comes to math and engineering and STEM. So we say M sub O for origin. Again, not very flashy, but certainly will do what we need it to do. And what we're going to do is take the product of the mass with its algebraic distance from the origin. Now, again, this is a tendency to rotate, and you're thinking if we're interested in center of mass, we would like to be able to set up some type of algebra that would allow us to figure out where we could balance the system, so to speak. That is, to neutralize the tendency to rotate. And so what we want to do is think about a translation like we did in college algebra, which would figure out, so to speak, the point on the real line where the system would be balanced. So we'll just say that this particular point will be X bar, which will be a notation we'll use. So we define X bar to be the center of mass for the system. So when we think about figuring out what X bar is algebraically, we basically translate relative to X bar and set the actual moment equal to 0. So this implies we translate the moment. So we replace, in this case, X sub I with X sub I minus X bar. So we want to solve for X bar such that the tendency to rotate is neutralized. So again, this is very simple and very intuitive, but it works out very well because this idea can be extended to the plane. And then from the plane, we can think of a more continuous distribution called a lamina and apply the same definitions, except what, as you well know, the sums will just be replaced with integrals. So again, we keep doing the same thing over and over, but we have to set the stage. And this takes just a little bit more time because it's maybe not as maybe simple, but simple is relative, right? So let's go ahead and solve this. Remember, this is independent of I. So equivalently, I equals 1 to n. So we'll multiply m sub I, x sub I, and then of course multiply here m sub I times x bar. So if you will, we just have a finite sum and it's certainly convergent, so we can write this as two sums. Just using the basic properties of the sum from pre-cal. We'll do a lot more with series in this class, maybe more than you would like, but this will certainly be a good starting point. So m sub I times x bar equals 0. Okay, so now what we can notice, if you will, we can go ahead and transpose this equation, just move this series to the other side, or we'll just isolate it. So we'll have the series I equals 1 to n of m sub I times x bar equals the series. And of course, that's this series I'm writing now is just the moment about the origin. And now, of course, the x bar is independent of the I, so we can factor it. Now, again, if you notice here, this is just the sum of all the masses in the system. We're thinking that's just the mass of the system. And so we'll have another notation for that too. So if we solve for x bar, we just divide by the mass of the system. So we can use our notation. Like I say, we already know that we've defined this to be the moment about the origin. And then we can just define the mass of the system to be uppercase M. So I'll go ahead and write this up. Uppercase M we'll just use for the mass of the system. And this will be a notation we'll continue to use even with the integrals. And of course, we'll have an area density like with the problems with work. We had a weight density because we were moving slabs of liquids around. So now we can see that there's a nice formula, okay? And you may have already seen this formula before in your physics class. So we see, so in summary, equivalently, just writing this over to the side, X bar is just the moment about the origin divided by the mass of the system. So that gives us an algebraic way to figure out the balancing point. Again, all algebraic, again, where the distances are algebraic. I mean, we sometimes call that a directed distance because the sign is not neutralized. The sign is important. When we study polar coordinates, the R or the radius or the radial distance will be directed. It just really depends on how the system is set up and actually which works best. All of the concepts and ideas that we work with have been tested, so to speak. And so conventions only arise out of a necessity for efficiency and completeness. So like I said before, you future engineers will have your own conventions and speak your own language like we speak the language of mathematics. Now, next, we need to take this concept and just move it to the plane. And that'll be very simple to do. So let's do that. Again, with this problem, what we're interested in doing is now putting the system of point masses in the XY plane. And doing a similar construction. So what we're going to do is simply now distribute masses in the plane and then notate distances to the X and Y axes. So we'll start out with an M1. Now, the thing is, I'm saying, okay, there's the mass right there. And I'm not putting the coordinates beside it, which I could be doing. I'm just notating the coordinates as to the distance to the axes. And so now this is where we have to think about what we're doing. The actual X coordinate is notated here, and the actual Y coordinate is notated here. So when we think about the point X1, Y1, this is exactly what it would be, but the distance here to the Y-axis will now be X1, and the distance to the X-axis from the point mass will be Y1. So let's just put several of these down for you to get used to looking at the plane a little bit differently. There are many times when we can take a little bit more time to think about what we're doing. So now we have a point mass y sub 2, and its coordinates are just x2, y2. And so again, and if you want, I'll go ahead and just stick this right here, just so you're completely sure of what I'm doing. So when we think about this, again, we have a point mass at a particular coordinate pair, and we have the distance to the y-axis, which is the x coordinate, and the distance to the x-axis, which is the y coordinate. Let's just write a couple more and then we'll do a general formulation utilizing what we've done here to, of course, be lazy. So M3, X3, Y3. And then of course, for some M sub n, I'll just put one in each quadrant just to give everybody an equal showing, so to speak. So even though this is a very simple construct, it is quite profound because it really is the essence of center of mass. So again, let me write here 2 dimensions. We're still discrete though. So this is, we can just call this part 2 or whatever. So the idea here is that we want to think about moments about the x-axis, or a moment about the x-axis and a moment about the y-axis. So now we can think, if we're trying to balance on the x-axis, that's going to necessitate looking at the algebraic distances of the y-coordinates. So this implies that the moment about the x-axis will now be the sum, as we've written before, masses times the algebraic y distances. And now, if we think about the moment or balancing on the y-axis, then we have to think about the algebraic distances of the x-coordinates. So you can always go back to this idea and kind of configure how things are set up. And it's important because when we develop the continuous formulas, then it will definitely be associated with how we orient the actual lamina and how we discuss its algebra. Because if we flip it around, we have to make that same notation flip with the formulas. So again, this is just a little bit more subtle than what we've done before. So now we think M sub I, X sub I. So now this implies that we want to think, okay, now instead of just a single real number, we want the coordinate pair that balances the system. So like if you had all of these point masses on a plane, and you know, you held it up, you would put your finger at the actual center of mass, and if you were actually there, then you could balance that actual system that way. I had some students several years ago to do a really interesting model with interesting lamina, so to speak. And the student, they all did the construction after they did their mathematics, and they posed for a picture holding up the model with a pencil. And you know, I thought to myself, well, that's engineering at work. So it can be done, and obviously is an important construct. So now we have the x coordinate of the center of mass will be the moment about the y-axis divided by the mass of the system. And the actual y-coordinate of the center of mass will be the moment about the x-axis divided by the mass. So these are very interesting formulas that are developed in the discrete case. Again, we'll think in this particular case as we balance, so to speak, about the y-axis, as we balance, so to speak, about the x-axis. we see how the formulas tie into these, but we have to really do a double take as to how the X sub i's and the Y sub i's are distributed. It's just a little bit different way of looking at coordinates in the plane. So we really kind of cheated and just said, now these definitions will make sense relative to what we've already done. And we will continue to hang on to these, okay? And then of course, if you want, in this particular case, we'll just go ahead and write this down again. The mass of the system, I know I've written it up at the top of the page, will be just like as we've said before, the sum of the m sub I. So that doesn't change. So now what we want to do is to take these formulas and to recast them with integrals. So a continuous distribution. And then from here on out, this will be what will drive us. So these are the standard conventional formulas. So we'll call this the continuous distribution. This is number 3. Continuous distribution. And we'll focus on uniform density for now. This can always be adjusted, but we want, and it's an easy adjustment, but we want to start out with uniform distribution. So what we'll say is we have a lamina. That's just the jargon for this, the terminology. Lamina in the plane of uniform density. We're saying it's constant, uniform density, and we'll use rho again. Okay, so remember, rho is not a P, it's a Greek letter, rho. So uniform density is where we're going to start. And we'll just basically think of doing areas back in 7.1 like you did on your first test. And we'll just say the lamina occupies the region bounded by the curves. So in this particular case, let me adjust this a little bit. And we'll take some vertical lines and we'll take an upper curve and a lower curve, just like we did with the areas. So in this particular case, we'll say that we have X equals A, X equals B. Again, thinking about limits of integration. And then we'll have an upper curve and a lower curve. So we'll have Y equals F of X, Y equals G of X. And for our purposes, we'll just assume that F of X is greater than or equal to G of X when X lives between A and B. So we're going to set up a system of formulas that will actually work with X as the independent variable. And, of course, if you have to switch it out when you're doing that with the methods we've done so far, nothing changes. But the moments will change based on how we compute them. We'll come up with a formula. So if our rectangle is distributed vertically, and if we were to move it to a horizontal position, then that would mean we would just have to make a slight adjustment with the moments, but it's not a difficult one, but it's easy to overlook. So let's go ahead and draw this. So in this case, we have an upper curve and a lower curve. We'll go ahead and mark off the vertical lines here. And X equals B. And we'll just take an upper curve, F, and a lower curve, G. Now, of course, we're going to think about a partition. That's always what we want to do. So again, we'll have a partition. A will be x sub 0, then x1, and then the ith subinterval. Same song and dance. By now, you probably could recite this in your sleep. Same thing we've done many, many times. And then, of course, we'll take a C sub I for the Riemann sum, any element in the ith subinterval. So now we can mark off a rectangle. And I'm making this a little bit larger so it's easy to see. And so now, of course, we have, in this case, C sub I, F of C sub I. And here we have C sub I, G of C sub I. Clearly, that's what we have, but we're gonna take these coordinates and get a midpoint of the strip. Now, just like we did before, we're going to use the uniform density to get the distance to the x-axis via the center of mass, so to speak. So first, we're going to say, okay, if we have uniform density, then the actual center of mass will be in the center, so to speak, of the strip. And so we can say, okay, well, how are we going to get the distance? Well, the midpoint of this strip will give us the distance to the x-axis. So now, and I'll put this in another color. So this distance will just be the midpoint. Remember, we add the coordinates and divide by 2. So this is very simple, but a little bit different from what we've done in the past. So that's the distance we're looking for. And then, of course, this is like doing the distance to the axis of revolution twice. The other one's actually quite simple. It's just C sub I. So, of course, now we have a distance to the x-axis and a distance to the y-axis. Now, of course, we need to think about, excuse me, mass of the strip, and we'll call that m sub I. So of course, if we've got a uniform density, we can just take the area of the strip and multiply by rho. So we've got what, rho, and then of course we'll have the upper curve minus the lower curve, and then of course let me notate here delta x sub I. So the upper curve minus the lower curve would give us the length, and of course the delta x sub I would give us the width. And if we hit that with the uniform density, that gives us the mass because the areas would absorb. So we get this. Very simple. Okay. So the idea here is that we're really using what we've done before. That's why this is later in the section. We've got these areas, the uniform density. So we're really going back to the area configuration that we did early on, which of course we have to use throughout the chapter, even if we're doing the volumes and all. It is just part of the scheme. And so now we can say, okay, well, if we're going to kind of add all of these up, we need to do this for the entire partition and then let the norm go to 0. So now we use the definitions for moments. So let's do it. So now let's just go ahead and look at the one where we're thinking about, in this particular case, the moment about the x-axis. So going this way. So we'll have moment about the x-axis will be the limit as the norm of the partition goes to 0. So we have I equals 1 to n. And then we get the mass. Again, in each case, this is always the mass. So we have rho F C sub I minus G C sub I times delta X sub I, and then times the distance to the x-axis, which is this fraction right here. Now, my notation is a little bit different from what's in the book when it comes to writing this formula, because I don't like to write extra stuff. Nobody does. So now we can look at this and say, as the norm goes to 0, all these c sub i's become x's, and then we get a dx here, and the 1/2 and the rho, they're constant, so they can be extracted. But then we have a difference of squares. We have the f minus the g times the f plus the g. So I just go ahead and write that as a difference of 2 squares. So now we get, and this is what's important, ladies and gentlemen, you have the rho divided by 2, okay? Students always forget the factor of 1/2, and it'll be a thorn in your side. So when you finish the lecture today, get out your note cards and just jot these down, just like you have a formula for the shell method. That way you ingrain them in your brain and you don't forget. It's like, shell method, we've got 2 pi. Disk method, washer method, we just have pi. So there's always something to forget. So we have rho divided by 2, a to b, and now we've got the difference of squares. So we have f, I'll just go ahead and be lazy, f squared of x minus g squared of x, using our sloppy notation, which is fine. So in the book, they just go ahead and write f minus g times f plus g, but again, that may be convention for the way the book was set up, but I always like to just go ahead and write it using the identity. So again, you see how we use what we constructed with the discrete case to make a transition to the continuous case. So it was worth it to go over that. And if I hadn't, none of this would make sense. Sometimes you've got to talk a little bit about the origins of formulas. Otherwise, you're manipulating things that without any understanding. And I don't really think that does anyone any good. And so now the moment about the y-axis will be the limit as the norm goes to 0. So we have the same sum, I equals 1 to n. And now, again, we have the mass. That doesn't change. So we have rho F C sub I minus G C sub I delta X sub I. And now this is what simplifies so much. The distance to the y-axis is just C sub I. So we don't have this complicated fraction. We just have C sub I. And now, of course, in the limit, the C sub i's are replaced with X. And then, of course, the delta X is replaced with dx. And then certainly the rho can be factored. So we get a simpler formula. So we have rho a to b, and now we have the x times the difference. So and let me just go ahead and put the m sub x and the m sub y, again, moment about the x-axis, moment about the y-axis. So not a surprise. And now, of course, the integral for the mass will just be rigging this as an integral. And I'll just say, and then we'll write the actual definitions for the center of mass. So mass will just be rho A to B of the difference. So that pretty much looks like this formula without the X. So the thing, it's like center of mass is like doing a work problem or a complicated volume for a solid of revolution. If you've got a lot of algebra, you just have a lot of separate pieces to compute. And of course, just like doing integrals or anything, the setup does take time. But again, that's what you do with these types of applications. Now let's go ahead and just summarize. What does this give us? So now if we think about this, this implies, just like we had before, we define the x-coordinate of the center of mass to be the moment about the y-axis divided by mass, doesn't change, and the y-coordinate of the center of mass is the moment about the x-axis divided by the mass. And so when you think about this, you look at this, and I might as well go ahead and put a box around this. It's not like it's unimportant. It's very important. When you have a continuous distribution, ladies and gentlemen, you are forced to compute these three integrals. Now, of course, if you're dealing with a geometric object that you already understand, for instance, if WebAssign gives you some objects and you think of that's a circle and that's a square, well, you can just treat that as a point mass, and you've got all the mass concentrated at the actual geometric center. So when we consider the fact that we have a uniform density, which is usually the case when we're thinking about centers of mass, we sometimes call the center of mass the centroid. Centroid, C-E-N, I'll just say this, centroid. That's the actual geometric center, which is the same as the center of mass, geometric center. So we think of the actual density as being precisely one, so to speak, or constant. You know, we can, if you're not really worried about, you know, the problem will always say you need to throw in the rho, even if it's uniform when you're computing the moments. But obviously, when you do the ratios here, the rho's absorb. Okay, so the coordinates are just real numbers. So, but it's still important, even if you're doing a problem and WebAssign says, okay, you've got a uniform density, you still have to put the rho in the moment calculations. If not, it's like leaving out the constant of integration. It will scan it and mark it wrong. So many times if we're dealing with maybe trying to find the center of mass of a parallelogram, we can assume that the density is just one and just kind of forget about it. Not a big deal, but in general, if it's not assumed to be one and it's just constant rho, we need to kind of drag it along and you know, just to keep our calculations legitimate, so to speak. So when we think about the center of mass, we often, like I said before, discrete cases, not too bad, fairly straightforward. We take the discrete case and we render formulas for the continuous distributions. And here we have them right here. So all of these just need to go into your memory bank, just like we did for the shell method or disk method, and just jot them down and practice with them. It's kind of like writing down trigonometric identities. Let's face it, the ones we use all the time, we know. And of course, the ones we don't, we have to either rederive or check our little chart of identities. Now let's try some of these out. The discrete cases are pretty simple. So I want to start focusing on some of the continuous distributions. And there's some really good problems in your WebAssign. I think you'll enjoy them. And like I say, because I derive these formulas for the discrete case, you can just look at that way with the products of the mass with the algebraic distance. And then of course you can just do your ratios and you're good to go, just like you would in a physics class. So let's look at some applications of this. Now, I will say this, when it comes to doing some of these, just like with the other problems, there's a fair amount of just algebra and then just arithmetic like we've seen. And don't look at it as being a drag, just say, okay, that's part of the process. So in this first problem, we have a lamina of uniform density. Lamina of uniform density rho. And it's bounded, and I picked one that has some quadratics. I know those give you good practice. And we'll say bounded by the curves, or just bounded by. In this case, we have y equals negative x squared plus 4x plus 2. And then we have the linear function y equals x plus 2. And then the question is compute the center of mass. So when we think about this, it's just, okay, this is like doing an area problem. We're going to do it just like we're in section 1 of chapter 7. Now, what we can first do, and this might just only be for aesthetic reasons. Let's just go ahead and know that the way this is set up, if we're actually going to have a problem, this quadratic opens downward. And of course, this is a linear function, so we pretty much know which one is the upper curve. But let's just go ahead and do a little pre-cal and figure out the vertex, just so we have a nice picture. Not that you have to have it, but it's good practice. So let's factor the negative. So we get an x squared minus a 4x. Of course, we'll leave some space, plus a 2. So again, we have the negative x squared and the positive 4x. And so we take half of the negative 4, which is negative 2, and square it. So we add 4 and we subtract 4. Just the same old routine we've done many times. So in this case, we get the negative. Here's our perfect square, x minus 2 quantity squared. And then, of course, we have the negative negative. So this will be 4 plus a 2. So we have plus a 6. So we just have a vertex of 2, 6, just kind of to make the drawing look a little better. And now, of course, we just need intersection. That way, with the intersection, we can determine our limits of integration. And so we have negative x squared plus 4x plus 2 equals x plus 2. So now, of course, let's just retire everything to one side. So we have a 0. So we get an x squared. And then we'll say x minus the 4x, which is a negative 3x. And of course, the 2's absorb. So this gives us, if and only if, 0 equals x times x minus 3. So of course, we'll get a value of 0 and a value of 3. So x equals 0 or x equals 3. So now, of course, we'll be lazy. So of course, if we have a 0 here, we get a 2. So 0, comma 2. And if we have a 3, we get a 3, comma 5. So let's just go ahead and get a little rendering of this. So we've got a 0, 2. So we'll say 1, 2, about right here. And then with the another thing too, you could like do the intercepts here and do half of that, but what we have is fine. And then we have a 3, 5. So 1, 2, 3. And then let's see, 3, 4, 5, 6. So we'll do a 5 and a 6. So a 3. And then we've got like a 2, 6. So about right here. So let's just go ahead and connect for the linear function. And then we can draw in the quadratic. Don't worry so much about the intercepts. It doesn't have to look perfect. So there's our, it's not Rembrandt, of course, so we don't need the intercepts, but we're fine. So now at least in this particular case, we've got our 3 here and our 0. So this point is 3, 5. And this is a distinguished point, 0, 2. So that gives us the 0 to 3. So we know that X lives between 0 and 3. And so now, of course, the actual lamina looks like this right there. And so we've got our upper curve. So we have y equals negative x squared plus 4x plus 2. And we have our lower curve, y equals x plus 2. So now all we have to do is apply the formulas. So again, this is think about this. This is like doing an area problem. You don't have to be, of course, as fastidious. I mean, when you're working on a test, you go a little bit maybe less beautiful. But again, the idea is that all of this is the same. And then we're going to calculate the mass, which is basically an area integral. So that's something we've done before. And the other integrals will be like doing a shell method or a disk method, for instance, where we have the squares. The other moment, like the shell method, where you have the distance to the axis of revolution and the height, so all of the integrals will look the same. You just have more to do. So now the mass, in this particular case, let's just go ahead and compute this. Nose itches, sorry. So now we've got, in this particular case, rho. And if you like everyone, you can go ahead and factor the rho. Just go ahead and put it outside, but just don't forget it. And then, of course, we have 0 to 3. And we have the upper curve minus the lower curve. So we'll just use what I've notated here. So we have minus x squared plus 4x plus 2, our original curve, minus the lower curve, which is y equals x plus 2. So this gives us rho 0 to 3. And so now we have a negative x squared plus 4x plus 2 minus x minus 2. So now we have rho 0 to 3. And of course, the 2's absorb. So we have a negative x squared. We have a what? 4x minus an x, so that's plus a 3x. Well, hallelujah. Fewer terms. We didn't have to square a trinomial, which can be a lot of work, as you've noticed. So now, again, let's go ahead and get the mass. Let's do the antiderivative. So this will give us a negative, add 1, divide by the new power. We're going to get a 1/3 times an x cubed. Go ahead and dress that up a little bit. And then, of course, we're going to add 1, divide by the new power. So we'll get 3/2 x squared, 0 to 3. So now we can go ahead and note that, of course, that the lower limit will annihilate everything. So we get rho. So we have negative 1/3 times 3 cubed plus 3/2 times 3 squared. And then, of course, the lower limit giving us the 0. And now what we can notice here is that we actually have a 3 cubed in each of these terms. And since we're lazy, we'll just factor that, 3 cubed. And of course, here we're left behind with the negative 1/3. And this leaves the positive 1/2. So we get rho, and of course, that'll give us a 27. And with a common denominator of 6, of course, this will give us a negative 2 plus a 3. So we have rho. Well, I don't, let me just go ahead and leave it alone. Let's just call this 3 times a 9, and then a 2 times a 3. And of course, the 3's absorb, and we have a 9 times a rho divided by 2. So that's the first calculation. Again, very simple, but very important. Again, what's so wonderful about chapter 7 is that it really does reinforce the concept of fancy arithmetic. I mean, that's all we do. That is all we do in calculus. You're saying, well, I'm computing a derivative and I'm doing antiderivatives and I'm doing limits. Well, it's all arithmetic. I don't know why it's ever been thought of anything else, but that's exactly what we're doing. So now, well, let me keep that nearby because, of course, we're going to need to use that again. So now let's go ahead and compute the moment about the x-axis. And then we're going to need the moment about the y-axis. So when we look what we have, let me cover this part up so we can use what we need from the given, and then I'll remove it. So now we want the moment about the x-axis. Again, remember, we've got an independent variable of x, and then we have the distance to the x-axis, which requires the midpoint formula. So that's when we get the squares. So that's how I want you to envision this. And of course, if we flipped it around, the formulas would flip between the two moments. So that's just something we need to think about in terms of our convention. So we have rho over 2, 0 to 3. And now this, got that trinomial again. Sorry about this. So we got the upper curve. So we have negative x squared plus 4x plus 2, quantity squared, minus, and I thought this would be a good one because it has a little bit of everything. And of course, if it were just 1 plus 1, you wouldn't need me. And then the lower curve, again, is x plus 2, quantity squared. So when we look at these particular calculations and we think about what we have to do, let's just go back to the formulation that we did. Instead of writing f minus g times f plus g, we just go ahead and write it as the difference of two squares. So you've got the upper curve squared here minus the lower curve squared, just to simplify things. So let's go ahead and reduce. I remember I was working with one of your colleagues, we were doing a cross-section method, and this turned out to be the case, which is, a little bit longer. So now let's go ahead and do it. So we square each of the terms. So we get x to the fourth plus 16x squared plus a 4. And then you just do them in pairs. So now we do the product here. We get a negative 4x cubed, hit it with a 2. So that's a negative 8x cubed. So that's the first two. Then let's do the second two. We take the product, that'll be an 8x, hit it with a 2. So that's plus 16x. And then let's do the outer two. So this will be a negative 2x squared, hit it with a 4, we get a minus 4x squared. Now, again, when you think about what we're doing here, the algebra is just as important as the limits of integration. Everything's important. So just like you did for your first test, focus on that. Now, of course, we have the minus here, and we've got the binomial squared, which is a little bit easier. We get an x squared. We get a 2x times 2, which is a 4x plus a 4 dx. So let's clean this up. 0 to 3. So we've got our x to the fourth plus 16x squared plus 4 minus 8x cubed plus 16x minus 4x squared. And now let's distribute the negative. So we get a negative x squared minus 4x minus 4. So now we want to collect some terms. So of course, the x to the fourth, that's the only one of those we have. So that's good. So that one's done. And now for the squares, we have a 16. And so this gives us a 12 in this particular case. So we've got the 16 minus the 4x squared. So that gives us a 12x squared, and then minus another one. So that gives us an 11x squared. So these are taken care of. I don't know why I did that one first. It was just second there. And then now for the x cubed term, we have one of those minus 8x cubed. And now for the x terms, we've got a 16x and we have a 4x, so that's plus a 12x. And then of course the 4's absorb. So like I teach my pre-calculus students, do a check, do a little arrow, do a little underline. That way your work is preserved and it's much better. You don't have to actually put everything right beside or juxtapose, but that way you have a clear roadmap of what you've done. And so we have x to the fourth plus 11x squared minus 8x cubed plus 12x dx. So let's complete this calculation. So now we add 1, divide by the new power. So we get 1/5 x to the fifth. Just go ahead and dress it up the best we can. Plus 11 over 3 x cubed minus 8 over 4 x to the fourth plus 12 over 2 x squared 0 to 3. And of course, saved again by the fact that we have a lower limit of 0. So that was good. It's funny, with one of your colleagues, the problem we were working, the lower limit, of course, was non-zero. So it was really interesting. Went on forever. So not only did we have to square a trinomial, but we didn't have the benefit of a zero lower limit. So when it rains, it pours, right? So now what do we get? We have 1/5 x to the 5th plus 11/3 x cubed minus 2 x to the 4th plus 6x squared, 0 to 3. Again, when you think about exactly what we're doing and how we manipulate what we do, we keep doing the same thing over and over. But that's good because as I've noticed, the most proficient math students practice. You just practice. And when you get out of practice, it's like you have to bring yourself back up. It's like when I do lectures or when I do music or whatever, people always know when you've been practicing because there's a certain amount of ease in what you do. But the thing is that, you know, we have responsibilities that take us here and there and everywhere. So like I said before, a little bit of practice every day will serve you very well. So now let's go ahead and substitute. So we have rho over 2. So we get 1/5 times 3 to the 5th plus 11 over 3 times 3 squared minus 2 times 3 to the 4th plus, well, and here's something where you can say, okay, I think about this, and you can see in where was this deal here? Sorry, that's a cube. I was making a point here that will retire, and so you're thinking we'll just go ahead and we've got a square there, so that's good. We'll be fine with this. Thought I'd factor that, but I won't do it. How funny. And then minus 0, of course. So again, substituting 3, so we get 3 to the 5th, 3 cubed, 3 to the 4th, and 3 squared. So now, of course, what we can see is that everything gets, at least has a 3 squared. So let me do a little sidebar right here. This will just be 11 times 3 squared. So that's an easy reduction, so I don't have to write another line. So permit me that. So now we get rho over 2. And I'll go ahead and factor this. At least that relieves us of the 1/3. So that's not a bad way to do it. So we'll do the 3 squared, which we have in each of the terms. So what does that leave behind? Well, this will leave a 3 cubed. So we have 1/5 times 3 cubed. Of course, this leaves the 11 behind. And here we have the 2 times the 3 squared, 2 times 3 squared, and this just leaves us the plus 6. So that's good enough. So now let's finish off this calculation. So this will give us rho over 2, and we've got a 9 if you like. Go ahead and write that as a 9. I don't think the 5 is going to absorb any of that. And so now we have a 1/5 times a 27, and we have a 11 plus a 6, that's a 17. And then we have a 2 times a 9, that'll give us an 18 with a negative. So now we have 9 rho over 2. And so what does this give us? 1/5 times 27, what, minus a 1. Well, that's nice. So let's see where that takes us. So we have 9 rho over 2, 5. So this gives us a 27. Of course, minus a 5. So we have 9 rho over 2, and this will give us a 22 over 5. So we've got 9 rho over 2 times, well, what, 2 times 11? over 5. So now the 2's absorb. And so we have a 9 times an 11, which is a 99. So 99 rho over 5. Now that calculation was a little bit more complicated, and you will find with the squares, just like with the disk method, this will take more time, but it's a doable calculation. So again, don't always think something's going to be easy or hard. Just know that it may be possibly a little bit longer. Now, let's go back. We want to do the moment about the y-axis. So let's go back to our formulas and write that down. So let's see, moment about the y-axis. So this will be rho 0 to 3. And now remember, we have the distance to the y-axis, which is just the x. And then we have the f of x minus the g of x. Well, we've done the f of x minus the g of x, but I'll just write it in anyway. We know what it's going to be, but I'll go ahead and write it in. So we have, in this case, f of x negative x squared plus 4x plus 2 minus x plus 2. So again, it's always good just to do a double check. Don't just assume that the formulas you wrote before, or at least the computations you did, were correct. Check them again. So this will be rho 0 to 3, and this will give us an x. So we have a negative x squared plus 4x plus 2 minus x minus 2. So this gives us rho 0 to 3 x. And then, of course, as we did before, the 2's absorb. And of course, the 4x minus the x is a 3x. So that gives us a negative x squared plus 3x, which was what we computed before, which is good. So that most likely means our mass calculation is correct. And so now, of course, with the x, we just distribute and we'll be ready to add 1 and divide by the new power. So this gives us a negative x cubed plus a 3x squared. Once we move past the formulas, again, just arithmetic. So there are a lot of steps that we have to check, every step being important. So now we get rho, add 1, divide by the new power. So we'll get a negative 1/4 x to the 4th plus 3 divided by 3 x cubed, evaluated from 0 to 3. So we get rho negative 1/4 x to the 4th plus x cubed, 0 to 3. So now let's just go ahead and do our substitution. Of course, the lower limit giving us 0. So this gives us a negative 1/4 times 3 to the 4th plus 3 cubed. So now, of course, we have a 3 to the 3rd in both of these, so we'll factor that. So that's a rho 3 to the 3rd. And of course, that will leave us with a 3 and the negative 1/4. So negative 3/4 plus a 1. Again, we extracted all of that. So we take all the big numbers out because it makes it easier for us. We're lazy. And if we're lazy, we want to make the arithmetic as simple as we can. Sometimes it's not always possible. But then this gives us what? 27 rho. And of course, that's just a 1 minus a 3/4, which is just a 1/4. Just do that in your head. So that's 27 rho over 4. So what we're seeing in general is that depending on how much algebra is involved in the problem, especially when we think about squaring the trinomial, there's probably going to be a lot more arithmetic, because in that case, you knew when you did the disk method and washer method, squaring everything and upping the powers always increases the amount of arithmetic that you have to do. So now what we can do is we can go back. Let's see here, where are all our calculations? Let's see here. So, oh, we've got them right there. Let me go back to the mass. Yeah, we got the mass right here. So now let's just tabulate, so to speak. So by definition, X bar will be the moment about the y-axis divided by the mass. So we have the moment here about the y-axis, which is 27 rho over 4, or 27 rho over 4. And then the mass, remember we did here, we just get 9 rho over 2, but we flip it. So 2, 9 rho. So we divide by the mass, so just go ahead and reciprocate it. That'll be easier. So now the rows go away, and we get 27 over 9 times 2 over 4. And that gives us 3 times a 1/2, which is 3/2. Now, let's see here. All these papers. Let's see here. So we've got, oh, that's the next problem. Oh, let me not confuse that. And then Y bar is the moment about the x-axis divided by the mass. But fortunately, that's still on the same page. I don't have to hunt for it. So that's 99 rho divided by 5. And then, of course, we divide by the mass. Here's the reciprocal of the mass. So that's 2, 9 rho. So this gives us the rows absorb 99 over 9 times 2/5. And so now in the 9, we get an 11. So 11 times 2/5, and that gives us a 22 over 5. Let's see here. And that, it's interesting because this, let me find the original. Here we go. So let's look at the original picture. And we've got like a 3/2. So here, 3/2, we'll just mark that off right there. Well, 1.5. So there's 3. The scale's really horrible, of course. It's not the best. And then 22 over 5, that's going to be 4 2/5. So say like 4 2/5, about right there. So when we kind of march up here, there it is. Now that's just an eyeball here, but there's your center of mass. So again, we'll just do our little arrow here. Reading off what I have here, 3/2, 22 over 5, center of mass. So what I wanted to do was a problem that just kind of had all kinds of kinks in it that required a little bit more work. So if you're doing a problem where the graphs are simpler and there's less algebra, it doesn't take nearly as much time. So these are all a function of the complication of the actual equations. And so I'm not trying to paint this as anything but what it is. I mean, the calculations can get long, not that they're overly difficult, but the length of it does make the problem more difficult. So now you can see that it is not a triviality to compute a center of mass. The algebraic construction, though relatively simple, requires a fair amount of arithmetic when you actually execute the problem for a continuous lamina or a continuous distribution. Okay, so what I want to do now, and I'm going to make a comment here, and it's important as you work problems where the independent variable switches. Just remember, if you're doing a situation where the rectangle is now, in this case, horizontal. Let me just give you an example of this. And here's an important comment. It's just not a matter of changing the X and Y, because there's a problem about a parallelogram that I want you to work on. And this will kind of guide you into how I want you to do it. So this will mean that we have a horizontal rectangle. So say that there's a WebAssign problem, and I'm thinking about this one. So let me go ahead and draw it. Always work on problems before I open the Zoom, and I'm always watching my computer clock as oh, it's time for class. So I thought about this. Actually, I woke up this morning and I said, I need to say something about this. I want to make sure that my students understand this problem. Now, the case here, it's just not a small comment. I want to make it, and so when you work on it, you'll know what to do. So we're going to have a parallelogram. The vertex, one of the vertices will be at the origin. So this is going to be analytic geometry. So in this case, you're actually going to compute the centroid, the center of mass, because we're just going to assume that in this case, P is identically 1. So we're going to do a centroid, a geometric center, which is really what we did for the last one. So we're going to compute the centroid. Okay, so that's an N there. Now, in this particular case, we have another vertex, which will be A0. Of course, A is a positive number. And then we're going to analytically construct a parallelogram with a B and a C. So in this case, let's see here, we'll do point here. Of course, this will be the C, and this will take to be coordinate BC. And then we'll move over the same amount, so like another B about right here. So it'll be right there. So this coordinate will be A plus B, comma C. Of course, we're just making parallel lines. Okay, so there's our parallelogram, x-axis, y-axis. Now, if you think about computing the centroid here, you think, all right, well, if I do vertical rectangles, that's a nightmare. I mean, you know what I'm talking about. You got an upper curve here that's different. Then you have a different curve here, and like, too difficult. I mean, you start breaking up integrals with the center of mass or centroid calculation, and then it really does get messy. And so we're thinking the best approach here would be a horizontal rectangle where you have a right curve and a left curve. Okay, so what we would do in this case, we'll say use horizontal strip or horizontal rectangle. So now when you think of it, the Y will live between 0 and C. So we're going to think of it this way. And I'm just going to help you set this up, and then you can finish it. So when we think about our rectangle here, just draw it. Just do a visual, convince yourself. So now we think of the geometric center of the strip. And so now you've got this curve and this curve. So now when you think about the moment about the y-axis, it basically turns into the moment about the x-axis when the rectangle was vertical. You see, and so now we get the y here for the moment about the x-axis. So those calculations interchange, but the definition of x bar and y bar is still the same. It's just that the calculations of the moments are different. We just have to make the adjustments. So I'll just say this affects the moments. So you just need to make sure that when you write them down, you're focused on the fact that the rectangle is horizontal. And so the square formula is going to involve, so this will imply, let me just write them down. This will, and you know, if you like, you can just call this curve f of y. And of course, you just figure out the curves using the 2 points make a line, and you'll get some nice, easy formulas. And trust me, this formula is not really hard, and the algebra does simplify. So we can call this f of y, and we'll call this curve g of y, okay? So if that's the orientation of the rectangle, then now this implies that the moment about the y-axis will now be rho over 2. In this case, and I'm being particular to this, 0 to c, and then we'll have f squared of y minus g squared of y. So that will change. But again, the x bar and the y bar are still defined the same way. It's just that we have to change the moments because of the orientation of the rectangle. And then, of course, this will imply that the moment about the x-axis will use the y, like the x in the previous case. So we get rho, in this case, 0 to c, y, f of y minus g of y. So this is the main thing. The sad part about this problem is that if you ignore this and you just jump right into it, then it's a nightmare. And you're thinking, what am I doing? So you have to realize that when we do this construction, it's just not a matter of saying, okay, you know, vertical, horizontal, no problem, because in the previous definitions, you didn't have a construct that was this complicated. You know, you dealt with one axis, and if you had to switch it, then you solved everything in terms of x, you know, or solved everything in terms of y, whatever. But now we've got two axes involved that are part of the same problem. And so we can't just interchange the x and the y and be done with it. So it's a much more complicated procedure. So, but again, what you did before is fine. Now we just have to make the adjustment. So this is exactly what you need in this case. Now when you look at this, let me just help you with the algebra, and then you can solve the equations to find the f and the g. So for like, let's just start out with the g of y. We'll do that first. So we have the very simple, but it's been a while, I'm sure, 0, 0, b, c. So again, this is just rise over run, right? So we have the slope of the line will be the rise, c minus 0, over b minus 0. Rise over run, which is c over b. So this implies now by slope point slope, there we go, y equals, of course, we've got two zeros, we'll be lazy and use that point. We have c over b x. Okay, so this equation describes that line. But now, of course, now think about a problem where we need to be with independent variable, because now, why? Because we've got a horizontal rectangle. So if and only if x equals b over c, y, just reciprocate. So if and only if our left curve, in this case, g of y, is just b over c times y. There we go. Now, of course, this is so easy. It's so easy, you think, oh, it's that simple. But it's the simplicity that makes the problem hard. Now what we can do, and we're thinking these are just shifts of each other. Let me do it in two steps. I won't do it as subtly, but let me just do it in two steps. When we look for f of y, we can just think of the fact that this line has the same slope, but it just is right shifted by a. So in this case, we can just say that y equals c over b times x minus a. Of course, we can think of the same thing here, but this might be a little bit easier way to look at it. So now we just take this line here and we do a right shift by a, so we replace x with x minus a. So what does this say? If and only if, in this case, x minus a equals b over cy, if and only if x equals b over cy plus a. And there we have a definition of our left curve. So right curve, f of y is now b over c y plus an a. Right there. So what you're seeing in this particular case is we just have to make a couple of adjustments to make this work. And I mean, this always happens when you think about calculus 1 and calculus 2. It's like, well, calculus 2 was so user-friendly. Well, now we're getting to all the topics that aren't necessarily user-friendly. So now you can take these curves here, you've got your limit of integration, and boom, right there. Do your moments, and then of course, here's a trick. What's the area? What's the mass? What's the area of a parallelogram? It's just base times height. You don't have to do a calculation there. So here's a hint. The mass is just the area, since p is equal to 1 or rho is equal to 1. Oh, don't let me say p, rho, sorry. This is just the area of parallelogram. So this is a simple, you don't have to do this. Parallelogram. And that'll just be base times height. So that'll be a times c. So that's another freebie right there. So here's all you have to do. Now I've set this up, do this calculation, and then x bar. In this case, this doesn't change. This will be the y moment over m, and y bar will be the x moment over m. So we don't have to worry about these. These are fine because we made the adjustments here in the formulas. So now I've set this up for you to finish on WebAssign. I think this is a really, really fun problem. And you see that the geometry, just like working with a triangle, and the center of mass or the centroid have these really, really nifty formulas. So I want you to think that you know, it's just not all toil with fractions, add 1, divide by the new power kind of thing. With this kind of problem, you're basically deriving a formula. And so once you have that formula, just like we use the formula for the area of a parallelogram, and then you're like, wow, look at what I can do. This is really easy. And so look at this problem as just an adjustment of the moment calculations so that you can now navigate a horizontal rectangle. So I thought this would be a fun problem. And then of course, ladies and gentlemen, if your rectangles are vertical, then this is not required. So you could actually be taught this section and never run into this. And then when you did, you'd be perplexed as to, well, why are my calculations off? I know that's not the center of mass, but I followed the formulas. So we do have to remember when we do mathematics, especially engineering and physics, is that do we have the hypotheses that are necessary for the formulas? Okay, we can't just, you know, throw caution to the wind and keep our fingers crossed. We want to know. I mean, I mean, if you're using the right formula and you make a careless mistake, that's unfortunate. But when you're just starting off incorrect, that's the worst possible case, and we don't want that. So use this to finish up that problem. I think you'll be very interested in the outcome. I think you'll enjoy this. Okay, and there's another, like I say, now you know how to navigate these problems, and there won't be an issue when you work into them. Now, this you're gonna shoot me. There's there's a nice theorem that I want to talk about, and you're going to say, "Oh, Professor Ron, we've been doing the shell method for the volume of a torus, and now you're going to do this to us." Well, when we get to calculus 3, we'll actually be able to prove this. And I thought, well, I might as well let the cat out of the bag and be, as I say, what does my nephew always say? Forthcoming or full disclosure. I don't want you to think that I'm okay. Here's what's going on. It's kind of like, this is the deal. It's called the theorem of Pappus. What is the theorem of Pappus? Well, again, this is one of these ancient results that was proven before the invention of calculus. And it uses the center of mass. And let me show you this. You're gonna really like this. This is called theorem of Pappus. This is the culture for today's lecture. I actually had a Cal 2 student when I was teaching an honors section to attempt a proof of this. She did a good job. I thought, this putting the cart before the horse, but she was really interested in it. So we did it. And I mean, I said, well, you can do it. And so I remember she actually couldn't meet with the class. So she gave me the presentation, and it was excellent. And now she took a break from school and is getting back into school. And so doing very well. So sometimes your schedule has to be amended a little bit because life happens. So we've got let R be a region in the plane and let L be a line in the plane that does not intersect the interior of R. Now, when I say that, ladies and gentlemen, the line could intersect the boundary. It could intersect the boundary, but it can't move in to the interior portion, okay? So it could just touch the region at a point. That's okay, like a tangent line, so to speak, in Cal 1. But it can't move into the interior, so that's important. And then let lowercase r be the distance between the line L and the centroid of R, the center of mass, or the centroid of R. And so you're thinking, as long as the centroid of R is fairly simple, this is going to make for a nice calculation. And then here we go, the solid of revolution formed by revolving R about L has volume 2 pi r a, where A is the area of R. So you're thinking, if you're dealing with objects that you really already understand, like a circle, And if you've got a circle of uniform density, you know, you just call it 1, you're thinking, oh, well, the centroid is, boom, right in the center. That's the geometric center of the object. And so you're thinking, wow, this is where you can utilize a theorem like this, which actually requires integration techniques beyond what we're doing. So when we have multiple integrals and iterated integrals, you can actually prove this. It's very reasonable. So, so here's an example of this where you're thinking, wouldn't this be something we could use if we were trying to compute the volume of a torus? Because to this point, what have we done? In your WebAssign and in the lecture, I used the shell method. Okay, and with the shell method, we had two major constructs. That is, we had to use the geometry of the situation to compute one of the integrals, which was half the area of the circle. And then, of course, we had to use an odd function integrated on a symmetric interval gives a value 0. So that involved quite a lot of machinery. I mean, that was not a simple problem. Setting it up, not so difficult, but then working through the algebra of the integration required that you kind of neaten things up and make some really, really important observations. Okay, well, now what we're going to do with this theorem, I'm going to show you a method that will basically doesn't allow you to do that or doesn't require for you to do that. So here's an example. This is from your WebAssign. Now you have another method. As my pre-cal students say, oh, here's a trick. Thank you, Professor Ron. I said, well, trick, good mathematics. So let's write this down. Revolve the circular region bounded by, in this case, we've got x squared plus y minus 7 quantity squared equals 9 about the x-axis. Compute the volume of the resulting torus. Now, of course, before, you know, because we had to use all this analytic geometry, we basically set it up so that, you know, we would just basically have a circle oriented at the origin to keep the algebra simple. But now with the theorem of Pappus, we can be a little bit more relaxed. So let's go ahead and look at this. Notice in this particular case, we have a circle. So we have a circle of center 0, 7. So center 0, 7 and a radius of 3. And we'll just say radius, I can't use little r because that's already taken, radius equal 3. So now let's just go ahead and look at this. So we're going to have to rotate about the x-axis. And so now when we look at this, we have a 7. So let's just say 1, 2, 3, 4, 5, 6, 7. And then we have a radius of 3. So 1, 2, 3. And then 1, 2, 3. We'll do the same here, just to get a picture. So here's our circle. Trying to look like an ellipse, but we'll do, there we go. There's our circle. And we want the region bounded. So basically we want to form a torus. So when we think about the torus and the volume, you know, in this particular case, you know, we can think about just the surface. You know, we know how to do area of a surface, but we want the solid. We want the surface and plus all the interior. So now when we look at this, let's just go ahead and fill some of this in. Area will be pi r squared. We have a radius of 3 squared. So this gives us 9 pi. And now notice the center of mass, we'll just say the centroid is just the geometric center of the circle analytically, which is 0, 7. And so now the distance to the axis of revolution, r, will just be 7. So I'll go ahead and tabulate that. So r, which is distance from centroid to the line, so to speak, to the line. So the line L in this case, this is L right here, equals 7. So when you think about this, just like, oh, okay, I'm saying you're taking the area of the circle and you're moving it around, you know, revolving, and you're living, your house is in the centroid, and you're thinking intuitively, this doesn't seem far-fetched at all, but intuition doesn't prove anything. But now you're thinking, okay, now we're set up for theorem of Pappus. So by theorem of Pappus, so you can go back to the calculations we've done with the shell method and try the theorem of Pappus. By theorem of Pappus, we'll have volume of torus, well, torus, not the automobile, but I don't even think they make those anymore. So we've got what? 2 pi r, 2 pi, r is 7. And then of course, A is 9 pi. So we get our pi squared that we, you know, had to work for before. So this gives us, in this case, what? Pi squared. And so we have a 14. So what's that? That's a, 10 plus a 4. Let's just break it down, times a 9. So this gives us pi squared. And so, of course, that'll be a 90. And then 9 times a 4, that's a 36. So that gives us a what? 126. So this is 126 pi squared. So you're thinking, Now, you think about this theorem and you're thinking, okay, well, that's easy. Well, if you know what a centroid is and you're familiar with center of mass, this can make some sense. But now you can think about what we're doing, what we've done in today's lecture, and then look back and say, okay, now let me take this machinery and go back to that problem that I did in WebAssign for 7.3 and see, oh, okay, go ahead and make the calculation. So what's nice about this, I remember doing a problem during my conference hours where we were using a shell method. And my comment was that, oh, look at this. Look at this. This is really just a right circular cone that we, what is it, made, so to speak. When you revolve the actual region, you generate a right circular cone. And so I said, well, let's just use the formula from geometry, even though that's cheating. I said, we did the calculus approximation, or actually computation, and then we checked with the geometric formula. Of course, we get the same answer. But I want to say sometimes, you know, when you're working a physics problem or an engineering problem and you notice a certain amount of symmetry, then you don't necessarily have to do the calculus part if you can actually get to the answer using things you already know. Obviously, in a calculus class, I need to see the calculus. But what you can see here is this is a very elegant way to get to the volume of a solid of revolution, as long as these computations are not too difficult. I mean, if it just means that you got to do all of these computations and they're, you know, difficult, like the problem we did before this or twice before this, then you're thinking, well, maybe this isn't as valuable. But as long as you have relatively understood geometric objects, this is a very, very beautiful result. So I suggest that you go back to the problems from 7.3 and try this out and compare your answers. I think you'll be very happy with the resolution. But again, just remember, mathematics is all about building scaffolding. And as you learn more and more and more, you look at problems differently. And so the next time you think about a torus, you're going to think about the theorem of Pappus. Okay, so go ahead and go to Blackboard and check out the solutions. I will be assessing your test work. And also remember and a lot of you didn't really notice this, for the entire semester, I have the same office hours. So you are always welcome at office hours. They are for you, okay? They are to help you. And I have office hours every day of the week. And so I will be doing 2 office hours today. One will be early and one will be later. And so go ahead and get the problems done if you haven't in the work, and then go ahead and mix in the center of mass to maybe get a little bit ahead. Now, what are we doing after this? Well, we're going to say, see you to the applications and step back into the process of doing antiderivatives. So we'll do a lot of review antiderivatives next class, just to kind of remind you of everything you know, and then parlay that into a method called integration by parts. So thank you for attending today. Don't go outside. I don't want you to freeze. This is the first day in a while I didn't run. I think with my Dr. Phil head, I would be pushing it. So stay well, stay inside, stay warm. Just remember, if you're inside and warm, you can do plenty of math. But I appreciate your attendance today, and I look forward to seeing you either at the conference hours or at our next class. Everybody have a warm day. Bye.